Hello everyone, welcome to Hydrography 2. Today we are going to talk about Module 5, which is titled Tidal Current. So if you remember from the second week of the Hydrography 2, I posed a question at MS Teams, and the question was simply, what oceanography phenomenon do you think happened because of the tide? And the best answer, or the answer that I was looking for, is actually the tidal currents. Okay, why does that happen and why that's the answer that I was looking for? We will talk about it in this module. So this module is divided into 5 segments. The first one, we were going to talk about the relation between the tide and tidal current to answer that question that I just posed you. And then the second, we are going to talk about ebb and flood, and especially the difference about it at a nearshore and an offshore environment. And the third one, sorry, is going to be about the linear and rotary tidal current. It's basically the idea of tidal current is different in one setting to another. And then we will close it with observations and analysis. So it's going to be a very well-rounded module. So the first one, of course, the relationship between tides and tidal currents. So we need to understand the terminology first. Of course, the tidal current is basically the horizontal movement of the water that accompany the rising and the falling of the tide. You can already imagine that whenever the tide is rising or falling, there is a body of water that is moving from one place to another. So for example, at flood state, or flood is actually pasang and ebb is actually surut. So this is pasut, flood and ebb. The horizontal movement of the water depends on what happens to the water level. Okay, so when the flood state is happening, when the water level is rising, then you can imagine that there is a movement of the mass of water from one place to the land, so from the sea inland. And at ebb, it's actually the other way around, so from the land going seaward. Okay, so that's basically the idea of tide, and that is why the tidal current have the same periodicities as the vertical tidal oscillation. So the idea is, if you can predict the tides, if you can measure tides and predict its properties, basically, if you can predict its characteristics, you can actually predict what will happen to the tidal current. But of course, it's only the tidal current. We are not talking about other currents that is induced by other force. It's only the tidal current. And I think it's more clear in this diagram. You can compare the top one to the bottom one. The top one is the elevation of the level of the water. So that's basically your water level, your tide. And then the bottom one is your current speed. And the time is the same. So you can imagine that these data are coming from two different instruments. Whenever you see something that is called the spring tide, here and there, so the spring tide is basically when the range of the water level is higher, and neap tide is basically when your range of water level is lower. You can see that, for example, in the spring tide, you've got 1, and then you've got -1. So you've got a range of tide that is 2 meters, but at neap tides, it's only about half. It's not always the case, but basically neap tides, you've always got a lower range of water level, okay? And the periodicity itself, at least in this case, between one neap tide to another, you've got a space of about 2 weeks. So you can imagine that this is actually a month-long observation. Okay, so at least at this area, in 1 month, you've got 2 spring tides and you've got 2 neap tides. And you can see the correlation in here. So when you've got more difference in the water level, then of course you will have more current speed because there's a lot more water that is moved from one place to another at spring tide compared to when you've got neap tides. Now we are going to talk more about flood and ebb. I think you already understand this, but I'm just going to repeat it. So flood is basically when the tidal current is moving inland that is caused by the rising of the water level. Okay, so it's the way you think is actually the other way around because the water level is rising because of those forces that you have learned a couple of weeks ago. Then there's a current that is moving inland. And the other way around, it's the same thing. So when the water level is falling, the water is actually moving seaward. Okay. And another terminology that I would like you to know is called the slack. The slack is basically when you've got the least or no tidal current at all. And it only happened just before ebb, just before flood, just before ebb. So basically, when the flood is changing into ebb, that's when your slack is. And it's very important to know when your slack period is because it's quite interesting to see that in your analysis. And another thing that is quite interesting is actually you can compare your tidal ranges and then your tidal currents to the wave of your water. Basically you will learn about waves more, I think, in another module, but basically when you're working at a near shore, you will have more tidal range, right? When you have more tidal range, of course you've got more tidal currents, but actually the wave itself is actually slowed down. So this is the equation. It feels counterintuitive, but it's actually true. So when you've got more depth, for example, if you're going seaward, then you will actually have more wave velocity because the wave is just flowing because there's no obstruction in there, there is no limitation in there, it just flows. But because of that, you don't have as much water level range, then you actually have least tidal current in offshore or in open water than when you go to the shallower water, because at shallow water you've got your seafloor as your limitation, which causes the wave velocity to slow down, and then it goes up, and then you've got more tidal range in there, and then you basically have more tidal current. Okay. Sorry. And then, for example, on continental shelf, the tidal current typically reach speeds of 1 to 2 knots, or it's actually around half of it is in meter per second. And the other way around, as I told you, in the open sea, the tidal current is actually less because the water is not confined. You have less limitation, a lot less. And in the open sea, the tidal current is been measured at a few centimeters per second. So it's quite big of difference. So another thing that is very interesting about the tidal current is its movement. So there is something that is called the linear tidal current and the rotary tidal current. You can actually read this in the book that is from the Open University. I think it's called Waves, Tides, and Shallow Water Processes. If you need it, you can just let me know at the MS Teams. So firstly, we will talk about the linear tidal current. So before we talk about this, you can imagine that this is your observation point. Okay, this is where you plant your instrument. We will talk about instrument later, but you can imagine that this is where you plant your instrument in the middle. And these are the tidal current. And these are the speeds. You can see the numbers, okay? Or actually, this is not the speed. This is the hours. Sorry for that. This is the hour. So this is at hour 1, 2, 3, and then you've got 4 when it's going back. You've got the slack, and then going back here, and then hour 7, 8, 9, 10, 11, 12, and it's back again. So in 12 hours, it's going that way and it's going that way. So if you imagine that there's a shore in here, can I do that? I think I can do that. So yeah, if you've got shore in here, then you've got your flood at hour 1 until hour 3. Okay, so for example, at 1 p.m. until 3 p.m. At 4 p.m., it's got the slack and it's going back, and the app happened. And at 9 p.m. to 10 p.m., it's actually going back here. So that's a very, very simple explanation about tidal current. But of course, it only happened in a restricted channel. This cannot happen in an open sea. So you can imagine this can only happen, for example, we are going to change our mind the other way around. So this is actually a river, okay? Well, it doesn't look like this, but imagine that this is a river, it should be something like that. That one should be bigger, and it's flowing towards the sea. Okay, so if it is the river, the movement is simply just like that. So when it's flooding, so it's the other way around now. So when it's ebbing, when it's going to the sea, it's going that way. And then when it's flooding, it's going that way, just like that. So half of the tidal cycle is one direction and half of the other is at the opposite direction. Now we'll move on to the rotary tidal current, which is a lot more common in the open water or even at the coastal or at the estuary or something like that. Why is it more common? Because you've got something that is called the Coriolis force. So the water is not actually going in and out, but it's actually going kind of round. So it's still the same, basically. At hour 1 until hour 6, it's actually going something like that. And at hour 7 until hour 12, it's going back. So principally, it's the same with this vector, but instead of going up and down in two directions, it's actually going in a circle, okay? So it's going up and going down, okay? So that's basically your flood and ebb. You can imagine it's basically, practically, it's still the same. It's still bringing water towards the land and towards the sea, but instead of going in line, it's going in a rotation. So more or less, it's an elliptical path rather than having a simple to and fro motion. To and fro is basically just front and back, okay? And the tidal current is, it is conveniently represented by diagrams, as I told you before, and in which the direction and the speed of the current flows measured at specific locations at intervals throughout the tidal cycle, okay? And recorded by arrows of appropriate length and plotted from a common origin. So you can go back to here, the hour is 1 until 12, okay? So that's basically, you can see that it's one tidal cycle. In here, this is actually also 1 to 12, but instead of having 1 to 12, it is actually pictured by +1 until -1. So high water is your, your HW here. HW is your high water, okay? So when the flood is in maximum, so when the water level is the highest, then it's actually moving here +1 of that high water, +2, +3, +5, +6 until it's back to the high water. So -1 is actually 1 hour before the next high water. So you can see how the movement is actually not very, very symmetrical. Why? Because you can see the trend in here. You can see how it looks like in the coastline. It actually affects what happened to the current. It's interesting to see that the current also follows that coastline, even out here. Okay, so that's basically what rotary tidal current is. Now we're going to talk about observations. Of course, this is the most interesting thing to do because we are Earth people. So observation methods, there are two. The first one is called the Eulerian, or if you're German, you can say that Eulerian, or if you're French, it's Eulerian, whatever. So basically in Eulerian, your instrument will stay at one fixed place. So if you go back in here, this is actually a Eulerian, a very, very Eulerian type of presentation because it stays at one place. So the instrument, it could be a current meter. This is a current meter, and it could also be acoustic Doppler current profiler, which we will talk about later. And the other one is the Lagrangian. In Lagrangian, it describes the flow as you follow the water particle. Okay, so you can imagine that there's a buoy or a current drifter or something that is floating uh, on the water surface, and then it follows how the water part, it follows like not actually one water particle, but it follows how the water flows, so you can see the trajectory. So for example, in here it might start in here and it ended up in here somewhere, and another drifter started in here and ended at somewhere in there. Or actually I think it's the other way around, because it normally you will put the drifter at one place and then it just flows somewhere. So you can see the example of the Eulerian method in here. This is your current meter. Your current meter normally has something that is called a propeller. Of course, you can imagine what happens to the propeller. Basically, it will record the water that is flowing through that propeller. Okay, this is actually a friend of mine. So this is, I think this survey happened at 2010 or something, or 2009. So yeah, this is my friend. Hello, and he's now working as a hydrographer. Oh no, actually he stopped. Yeah, he was a hydrographer. Now he's not working. He's working in the office now, of course. And then this is your ADCP. Um, when you're talking about the current meter with propeller like this, you've got your propeller as your main component, right? But the key component in the ADCP is acoustic beam. I think you have learned about acoustic beams in the last hydrography class, which is Hydro 1. So instead of having a propeller, you've actually got your acoustic beam that is pink to the water, and then you will actually track the water particles in the water, okay? And that's basically how you track the speed. So you can imagine ADCP is actually very, very good at the water that has more particle. Yeah, it's rather counterintuitive, but that's actually how that works. So another thing that is quite important or quite interesting is actually something that is called mooring operation. So mooring operation only happens at deep water. So what is this? Okay, MAB is meters above basement. Okay, so it is actually measured. It's quite unique when you're talking about mooring, because you're not measuring it from the top to the bottom, but you're actually measuring it from the bottom to the top. So that's actually 250 meters above basement. It's still pretty shallow in deep water operation, but still it's quite interesting to see. So this is your flotation technology. You want to know where your ADCP is, okay? And then you've got something that is this is your ADCP. This is where you want to see the speed of the water. So it's actually looking to the top instead of looking to the bottom. So you've still got a lot of water in here. The flotation is only to make it stable. And then there's the weight, of course, and you cannot do it with your hands, so you need an A-frame. to attach everything in one go, and then that's it. And this is called the acoustic release. This is where acoustic release is actually a quite interesting component. So acoustic release would be somewhere in the middle of this, probably. It depends on what project you're on. And the acoustic release idea is you just send a signal, and then everything in here will float because of this flotation. Okay, when you float, when everything is floating, then you can recover your ADCP back. Okay, so when you're moving it down, you just put it down with your A-frame, with the weight and everything. But when you want to release it from the ocean, then you need that acoustic release. So it would make no sense if you deploy your ADCP without deploying your acoustic release, because you will not recover that ADCP ever again. So the other one, of course, is the Lagrangian. Instead of deploying one instrument in one place, you can deploy one instrument and then follow its trajectory, which is quite interesting. And of course, when we are talking about drifter, it's a lot more interesting when you've got more than one drifter. So you can see, oh, okay, this is moving that way, this is moving that way, and then you can calculate what is actually happening over the sea. So that's when we are going to the data analysis. So the basics of current analysis is that we are measuring speed and direction of the flow. Okay, speed is q, and the direction of the flow we can define it as theta. Clockwise from the north, it's basically just like azimuth. And then we can work with the Cartesian coordinates of the current components. Okay, so positive north is v, and positive east is u. Okay, and the relationship is quite straightforward. You can actually see it from this diagram. So basically, your speed is your vector, okay, your q, and then your flow here is your flowing direction. Okay, so you can see those parameters in three types of analysis. The first one is time series. What time series is basically an analysis at a specific period of time. It could be in hours, it could be in days, it could be even in years. So the x-axis in the time series analysis is always the time, however long or however short it is. And then there's also a pattern analysis. So both this time series and pattern analysis are analysis that happened only in one station. Okay, so mostly it is used in Eulerian type of measurement. Okay, so you've got your time series and then you've got your pattern. So for example, here you've got a pattern of around north and a bit south. So you can imagine maybe that this happened because of the shore. So for example, maybe this is how the shore looks like. So that's why it looks something like that. Or is there any other thing that makes it behaves that way? And also an interesting to see here is the scale itself. The scale in here is this one is actually the furthest, not there, it's here. The furthest circle here is 2 meters per second. So you can imagine that the velocity in here is quite huge. You can imagine when that happened, why that happened, etc. And the last one is, of course, a spatial analysis. So a spatial analysis, you cannot only do it in one station. So either you can do a model or you can do it from the drifter data. So this is a time series sample. This is an ADCP station. So for example, this is your acoustic source. This is where your beam starts, okay? And this is the first bin, okay? This is the first reading. So the resolution of the data is maybe a tenth of this bin. So in 1 meter, you've got several data. So in 1 meter, you don't only get one data. You actually have a couple of data in here. You can see the contours, and then you can see another bin in here that has another data, and so on. And this is your water level. Okay. Okay. So what these arrows are, those are basically the factors that I've just told you in the last segment. Okay, so if we could go back a little bit, this one. So these factors are these arrows. So the directions are actually your flow direction. So for example, here up, it means north. Here, it means south. So you can see how it moves here, and then it moves to the south, and then it moves back a little bit slanted in here, and then to the north again. And the deeper it gets, the slower it is, because here is actually your scale. So this long is about 1 meter per second. So you can see here, this one is very, very close to 1 meter per second. This is probably like 0.8. And this is, you've got the slacks in here. Okay, and you can see what I told you before. So there's a slack period in here, and there's a slack period in here, and this is your high water. High water is basically the peak of each of your waves. At high waters, I will make a window of 25 hours. So 25 hours. Normally, when you've got like one peak and like, it's almost like one peak and one trough in 25 hour, and then we will focus on that. So if we focus on that, you've got your high water in here, which is that one. And then you've got your +1 until +6, and then -6 until -1. So that's what we talked about in the rotary cycle. You can see that the first cycle here is around 130. 130 means around here. And then it goes to 94, and then it goes to 43, 16, and so on. So you can see that the cycle in here is actually moving sort of that way. And then this is basically your current speed. You can see that the speed, the highest speed in here is that bit at +4 hours. And then you've got the slack at -4 hours. And then you've got another high water in here. So that's basically how you see the variation of the speed. And you can also see how the second cycle behaves. Apparently, the second cycle, the highest current also happened at a similar time, and the slack also happened at similar time. So there's a lot of things that you can already see from that 25-hour window. The next one is your pattern analysis. I told you already about what this factor dot plot is. Simply, that's your speed, right? So this is your 2 meter per second, and that's basically your azimuth. You can do a lot of analysis from here, and you can also see your current ellipses. Your current ellipses is basically, you can see the components or the tidal components that governs your tidal pattern. Okay, I'm not going to talk more about this. You can have a look at Pugh and Woodworth 2014 if you're interested in this. But the message of this slide is basically, you can see what tidal components that makes that governs that tidal current. Okay, and what are the most prominent component at that time? And the last one is going to be your spatial analysis. So I told you before that it's a lot better when you've got more current drifter, when you want to see a spatial analysis from a data, not from a model. So this is basically the global status of the drifter array. This is owned by NOAA, or by the American National and Oceanographic and Atmospheric Sciences Office, I guess. And this is how it looks like when you plot the data. It's very interesting to see how the current speed in here is, a lot more than what happened in here. And of course, you know what it is, hopefully. And actually, that could also spark a question in your mind. So this is the references. I can share the books to you if you want. You just drop me an email. You've got my email at the first slide. And if you've got any question about this module, you can always ask me. And I hope I don't speak for too long. Sorry that I didn't manage to cut this into segments, but hopefully you can understand what I'm saying. And these are the websites that I took mostly the pictures of. So you don't really have to read everything in the website. I was just looking for pretty pictures. So that is it for me. If you've got any questions, again, you can always ask in the MS Teams or you can ask to my email. Good luck for your future studies. Bye.